Welcome to the April 2019 meeting of the Houston.net Users Group. You're welcome to join us in person for pizza, prizes, and networking on the second Thursday of every month. Our meetings are hosted by Improving Houston in their office at 10111 Richmond Avenue, just inside the Beltway in Houston's West Chase District. You can check us out for meeting notifications on HDNUG.org, on Facebook, or on LinkedIn. And now, a word from our sponsor, Teals.
If you work in the tech industry, you really should volunteer for Teals, because without your contribution, without your help, there really won't be any other developers.
Whatever field or career that you're in, whether it's teaching or not teaching, it's your responsibility to give back.
There is a time commitment involved in the volunteering process. I think the rewards are definitely worth it.
It's the best part of my day. I would spend more time if I could, to be honest.
You should volunteer with Teals because you have the opportunity to help change a student's life.
And now our featured speaker, Aaron Stannard, will talk to us about ACA.NET and the future of distributed application development in .NET.
All right. Well, thank you all for coming today. I really appreciate it. This is my first time presenting at the .NET Houston meetup group. I recently just moved here from Los Angeles about 18 months ago, and everything sound good? Okay. I just moved here about 18 months ago from Los Angeles. I run a small company called Petabridge. We basically provide consulting, training, and support for ACA.NET, but really what we help companies do with ACA.NET is build large-scale distributed systems. So our customers are in fields like energy, finance, logistics. So we have a lot of companies that do things like ship cargo and use ACA.NET for building big IoT systems and that sort of stuff. My own background with ACA.NET is that I'm one of the co-founders of the open source project. I kind of created it out of necessity. I was running a marketing automation and analytics startup that I founded in 2012. And in order to build our marketing automation product, we needed the ability to build essentially a real-time stream processing system. And at the time, there weren't a lot of options available for doing that in .NET. Now there's a lot of options for doing it, ACA.NET being one of them. So what I'm going to present to you tonight is a little bit about ACA.NET and the role I think it's going to play in the future of building distributed systems with .NET. So we'll go ahead and jump right in. So a quick show of hands for everyone who's here in the room. Who considers themselves to be a back-end developer, meaning you do ASP.NET, WCF, Azure? Okay, so a good chunk of us. Now, if you don't do back-end development, don't worry. This will still have some useful, valuable information for you. But really, kind of what this talk's really geared towards is the types of business pressures back-end developers are being subjected to in the workplace. There's a lot of expectations being thrust upon us by industry, by our customers, by stakeholders, by other departments within our company. And here's essentially what we've been asked to build over the past 10 years. Downtime is no longer acceptable. You can't have maintenance windows in your business applications and not be treated like a complete joke by everyone else. So your applications are expected to be available 24 hours a day, 365 days a year. So we have this availability requirement. But on top of that, we're now required to support a much larger range of end user experiences than we had to before. iPhones being a good example. Or having to support IoT devices, or having to build programmable APIs that others can access via REST or WCF or SignalR or something like that. On top of that, we have other new form factors like TVs and watches that we may have to support too. And that puts a whole bunch of additional constraints on us we didn't have before. But the biggest constraint is the fact that the internet is becoming a bigger and bigger place all the time, and the volume of data that we are expected to capture, process, retain, and then transform into business value is always getting bigger and bigger and bigger. And we're collecting that data faster, and we're expected to turn around business value even faster all the time. Essentially, we have to do everything better all at once. So the ultimate sort of pressure that we can kind of give this thing a name to is scalability. It's scaling our domain, but also being able to scale our application's ability to support all this additional complexity without sacrificing speed and consistency. This is hard. And what's really hard about it is that all of the obvious ways to do these things are inherently wrong. I'll give you some examples from my own experience learning these things, but by trial and error a few years ago. So this is a pretty standard enterprise application architecture I'm putting on screen here. This probably looks pretty familiar to most of you. This is what, by and large, most enterprise applications have looked like for 3 decades now. We have a load balancer that takes requests directly from end users, some customer-facing web applications running on web servers. They primarily use SQL Server to persist their state. That's kind of the source of truth for this system. And then we might have a secondary replica in case the first one fails over. And then we have our back office stuff needed to support other members and other stakeholders of our companies. So this is like business intelligence, analytics, or maybe like an internal admin dashboard for like our customer service teams. In order to go ahead and do things like put a customer's order on back order or something like that. So this is a pretty standard enterprise architecture. Well, what's going to happen if we have a gigantic surge in user activity? So suppose, we've been running just a web application for most of our business's history, and we decide we're going to go ahead and add a beautiful iPhone application and Android application. And all of a sudden, even though, we went through all this trouble to try to go ahead and support it, that application is much more popular than we ever expected it would be, and our existing customers are using our services a lot more than they were before, and we have a bunch of new customers joining at the same time. Where is pressure going to build up inside this architecture? SQL. It's always SQL, in terms of where your scalability problems are usually. SQL is the obvious bottleneck inside the system, and you can just tell by looking at where all the arrows are going, right? And the reason why SQL is the bottleneck is because this is a highly centralized design. All the source of truth is consolidated physically in a handful of nodes, and we can't easily scale those in this architecture. So what's the obvious solution for trying to scale our way out of this problem? Well, sorry, go ahead.
Distribute the database.
Distribute the database. We're going to shard it. We're going to take what worked for one piece of architecture, and we're going to go ahead and partition it across multiple replicas of itself, right? So the range of data owned by this partition right here, the one on the far left, is going to be different than the partition of data owned here. So the customers in this partition aren't the same as the customers in this one, right? It's kind of like how a SQL Server federation works. And so then we have a coordinator sitting in front of it, and our applications talk to the coordinator to figure out which shard owns which piece of data I need for this request. This is the obvious solution. But this obvious solution has 2 fatal flaws that ultimately make it not ultimately the right solution for our problem. The first problem the solution has is there's downtime inherently built into it. If a primary node fails over, one of the 2 secondary nodes has to elect itself to be the next leader of that partition. During that period of time where there is no leader, no transactions can go through to that partition. And in a really busy system where you might have tens of thousands of transactions per second, that's actually not insignificant anymore, right? These are problems that you start to see at scale. Well, the more insidious problem that systems like this historically have had, they're a lot better now than they were, back in like the early 2000s, is that they're brittle. What would happen traditionally in one of these systems if we had a network partition right where this red line is, meaning the nodes above that red line can't talk to the nodes below it? Given the leader election algorithm bit I just described a minute ago, what do you think might happen in this scenario? Split brain, that's exactly right. What happens is what's called a split brain partition, where 2 different nodes both believe they are the source of truth for that set of data. Now, what can occur in a split brain scenario that might really impact our business really negatively? I'll give you a simple SQL example, since that's kind of what we're talking about. If we're using auto-incrementing IDs as our primary keys, can we guarantee that the primary key value in this database and that one are going to mean the same thing? No, right? So that's an example of data corruption caused by a split brain. You can also have data loss and other issues like that as well. So this is a really insidious type of what's known as a consistency problem in a distributed system. Now, I'll give you another example of a scaling problem that back-end developers are running into more and more as they have to start adopting these more sophisticated and more modern business requirements. So let's suppose, for instance, you get a requirement for a customer to support real-time push updates on the website over something like SignalR. Or maybe you want to have the ability to send a customer a push or an email notification in real time, right? Kind of like a reactive system. Well, if we're using a CRUD architecture, like what we had before, what we're basically going to try to do using this sort of state machine is say, okay, so my algorithm is, as events are being generated by an end user, I'm going to go and check to see if this user's generated these 4 events I need to send them a notification. So for instance, if this user does these 4 things, we might go ahead and proactively send them an alert or maybe an offer or a discount. It kind of doesn't really matter what the notification is. This is the algorithm we need to run. Well, the way we try to implement this in CRUD is using an algorithm called read after write, which is where you do this. Every time an event comes in through one of our web servers, that event gets farmed down to one of the web servers, and we write that event into a table that belongs, a set of entities essentially that belongs to this user. So we say, okay, this user has observed event 0. Then we try to read back all the events that user's done so far, right? And we say, okay, I just wrote event 0, and I only see event 0 back as soon as I read that data from the same table I just wrote to. Then when we receive event 1, we go ahead and perform the same read operation, but now there's 2 events there, right? Y'all can kind of see where I'm going with this. The idea being at the very end, when the final event that we're waiting for finally comes in, we go ahead and we see all 4 events are sitting there waiting for us in SQL Server, and we can finally fire that notification to the end user, and we've done our job, and everything is great. Well, the reality of how this system actually works is that even with a strongly consistent database like SQL Server, the concurrency and the latency of the tiers running above it are things SQL Server can't really help us account for. Every time we go and write an event and then read those events back, there's no guarantee necessarily that we're going to get all 4 of those events at any point in time during this series here. Because it's totally possible that 2 events can be written simultaneously to, let's say, depending on kind of how you structure your tables and everything else, 2 events that we both need can be written simultaneously, and at the time we execute the read, each process that's kind of competing for getting that right might miss the other. And we tested this really heavily at my last company before we developed Akka.net to solve this problem. And even in an environment with 0 latency, we're running everything locally through local Ethernet, there's no randomness or anything else involved, we can get the system to fire about 1% of the time in our environment. Not a very good business result, given that this is what generates income for us at our old business. So a lot of the obvious solutions to these sort of modern scaling problems and demands that our customers are putting upon us break down like balsa wood tables under not a very huge amount of stress. So fundamentally, distributed programming is harder than it looks when you have to start doing things that are a little bit more sophisticated than traditional sort of CRUD programming. And why is it hard? Well, in short, the fundamental thing that makes distributed programming hard is that it is stateful at its fundamental core. Most of our experience as backend developers, and I can say from personal experience, mine has certainly been like this, we've outsourced all of our state management problems to the database typically. But when the database can't do everything we need it to do anymore, now we become responsible for managing that ourselves. And that requires us to go and build up a whole bunch of muscles where we didn't have any before. That's really the first major problem with distributed programming, is we have to become responsible for managing state in a whole bunch of areas where we didn't have it before. The next big problem is that back-end applications are inherently concurrent with the way they're designed. Even a simple web server is a concurrent application, right? You don't serve requests serially. You have lots of requests coming in and you asynchronously try to complete those. That's concurrent programming. Well, doing concurrency and state at the same time is a really tricky thing. That's where locks and semaphores and critical regions and reader-writer locks and all these other synchronization mechanisms that you might have learned on the job or maybe in a computer science class. That's where we have to start using all of those. And even the experts screw those up all the time. Because it's not something that's intuitive or easy to reason about. It's very difficult to get right. And the other sets of problems you have to worry about in a distributed system, dealing with errors, dealing with topology, meaning knowing who's available to do work and who's not inside my system, are things that require us to expose a lot more sort of information about how our application's built to the code itself. Long story short, there's a lot of concepts that we used to not have to deal with directly that were handled by a lot of the products we used, like SQL Server and IIS, that we now become responsible for when we need to go and build these systems. And trying to tackle all that complexity at once can be really overwhelming. That's why we need some better tools to go and try and build distributed systems like this. Oops. And that's what we're going to try to provide to you tonight with Akka.net, is an example of one tool we can use, not the only tool, but a tool we can use to try to build some of these distributed systems that can scale, can handle errors gracefully, and can go ahead and perform some of these types of real-time processing you might need to do in the future. So the things we're going to try to cover tonight, I'm probably going to give you a condensed version of it since I don't want to keep us here until 9 o'clock. But the first thing we're going to take a look at is stateful application programming, the role that state can play in building some of these highly available, really fast, really reliable applications. We'll talk a little bit about protocol-driven design, which is essentially designing communication protocols between the different services and parts of your cluster. And one of the really important things about protocol-driven design is it explicitly describes what to do when things fail or what to do when things time out. One of the things I tell people when I'm training them in one of my courses, that we teach at Petabridge, or when I'm training one of my employees, is don't let it be an accident, is the phrase that I use. Meaning, if you anticipate that something could go wrong in your system, you need to have an explicit plan for what you do with it. Because a lot of the times what I see developers do is they just go ahead and just say, oh, well, that's probably not going to happen, so I don't need to think about it. And that's how you end up with, for instance, we have some customers in banking and so forth. That's how you end up with, let's say, a credit into an account that never posts. Or you end up with an error in reconciliation later. It's because someone basically cut a corner around something like that. Protocol-driven design is intended to be an approach that will help us address those types of problems. Next, we'll talk a little bit about fault and resource isolation. Decentralized architectures, avoiding all those problems of that SQL Server-based architecture we saw earlier. And then we'll also talk a little bit about the CAP theorem, which is essentially a way of making decisions about how to trade off one set of benefits for another inside a distributed system. So let's talk about the actor model. Now, this is Fabio. It's not the actor model we're talking about, but we tend to abuse his likeness pretty frequently in our presentations. The actor model is actually a really old idea dating back to the early 1970s. The original actor model white paper is only 2 years younger than the original relational database white paper, just to give you an idea of sort of how far back it goes. The actor model was originally developed as a way of doing concurrent programming when computer scientists thought that computers would evolve in a direction where it was tens of thousands of very low-powered CPUs in a giant warehouse-sized computer. Now, Moore's law saved us from that future. We ended up with a bunch of very small, very powerful CPUs instead. But where the actor model has become resurgent again is in the era of cheap cloud computing, where it's really easy to get access to additional compute power and hardware on demand. The actor model gives us a programmatic structure that makes it very easy for us to reason about all that additional hardware and for the ability for your application to sort of dynamically take advantage of it. The core thesis of the actor model really stems from its first major implementation, which was the Erlang programming language. Erlang originally stood for the Ericsson programming language, because Ericsson was the company who developed it. They started working on Erlang in earnest in 1987, 1988, as sort of the software backbone for the first digital telephone exchanges that they were building at the time. So a lot of your cellular traffic passes through Ericsson hardware that is built on top of Erlang, because they needed the ability to go ahead and make sure that as these cell networks grew and grew and grew, that they could go ahead and scale out those systems by just throwing more hardware at the problem, not trying to re-architect them every 12 months as the number of subscribers on the network increased, right? So the fundamental concepts behind the actor model, and I apologize for everyone who came to the North Houston meetup group last month because I'm stealing the slide from that presentation. The first big idea behind the actor model is that an actor is like a little microprocess, essentially. And actors are considered to be a fundamental unit of work. So an actor kind of executes its work serially, one message at a time. So actors communicate with each other by passing messages back and forth. That's true whether the actors are running locally, all inside the same process, or remotely, where they might be running on different processes on the same computer, or different processes on different computers. In which case, they pass messages over a TCP connection, typically is what they use. So this message passing back and forth is what makes actors fundamentally asynchronous. When I send an actor a message, there's no guarantee that actor will process that message immediately. That actor will process that message in the order in which it was received. So every single actor kind of has a little queue of messages that it works through. So it processes them in, first out order, kind of typically from what you'd expect from a queue, right? On top of that, messages in Akka.net are always immutable. So who can give me an example of a type in .NET, one of the built-in types that's immutable by default? String, exactly right. So why are strings immutable? Well, when I call the to-lower function on a string, I'm not modifying the original string. I'm creating a copy of that string, converting that to lowercase, and then returning that. So what immutability gives us is the ability to avoid, in a concurrent system, what's known as a side effect. Meaning, if I go and broadcast the same, let's say, piece of data to 1,000 actors, and all 1,000 of those actors try to modify that piece of data, what they end up doing is they end up creating their own copy and modifying that. So the other, let's say 999 actors all still have their original copy of that data they can work with. So that's basically why all messages are immutable in Akka.net. Now, in terms of what actors can do, like how do actors actually do work and how do you actually write code that can do anything useful with them? How does that actually happen? Well, what actors can do is they process messages. The fundamental way to think about an actor is it's basically just a set of message processing instructions. And in Akka.net, messages are defined as C# types, right? So I go ahead and say this actor can process a type foo or a type bar, and I'll use totally different functions for handling each one of those different message types. In addition to being able to process messages, actors can also create children. They can go ahead and create a child process, essentially. So one parent actor can have a bunch of children running underneath it, and it can go and delegate work to some of those children. Or it can maybe route messages to certain children depending on what the message's type or content might be. Actors can also change how they process messages while they are processing them. They have the ability to do what's called behavior switching. This is really useful in a distributed system because it allows you to create state machines, which is really useful for doing things like stream processing. Suppose, for argument's sake, I'm building a stream processing system that's analyzing data coming in from an oil well. Let's say I'm looking at production metrics. So I can see, volume numbers, temperature numbers, that sort of thing. Well, if I'm an actor and I'm processing data for a single well, and I notice a very sudden change in the types of numbers I'm getting back, I might go ahead and change my behavior to a state where I'm firing off warnings, and while all the messages are within a certain threshold saying, either the sensors are busted on this well, or there's something that's gone really wrong with it. Like maybe the pressure's dropped too much, and we need to send some technicians out there to see what's going on. As soon as those numbers return back to what their expected range are, I can go and switch my behavior back to just processing the messages normally without firing off any alerts or warnings. That's an example of behavior switching in action. And there's lots of other sort of simpler examples too. But I think given that we're in the Houston area here, I thought that'd probably be kind of relevant. And the last big thing that actors can do, and this is really critical to our discussion tonight, is actors can have state. Now, state inside an actor is just as simple as having a private field or a private property in C#. Actors are just a class you declare. but that state can't be directly accessed or modified by anyone else. The only way you can update an actor's state is by sending it a message, and that actor has to go ahead and modify its own state when it processes it. So there'll be some big implications for that in a moment. The next thing that actors do is the actors make a few fundamental promises that you can rely on in the design of your system. The first process, and the most important, is that actors are serial. One actor can only process one message at a time. So if actors can only process one message at a time, what does that imply about their state? Well, it means that all state inside an actor is guaranteed to be thread safe automatically, because it can't be concurrently accessed at all. So that's one of the first things that actors really try to solve, is concurrency problems. We try to eliminate the need for you to use synchronization mechanisms like locks. Instead, if the state is protected by the actor's mailbox, which is the thing that guarantees the actor can only process one message at a time, it means that that state is going to only be updated serially. And it makes it much easier for us to solve all manner of consistency and concurrency problems inside a distributed system. The next promise that actors make is that messages are processed in the order in which they're received. First in, first out, otherwise known as FIFO order. That's really useful because if I want to go ahead and make sure, let's say an actor processes, let's say 3 transactions in a row. If I'm building a banking system on top of Akka.net and I want to go ahead and tell one, let's say I have one actor that owns one bank account. I want to have that actor receive a deposit and then make a transfer, and then I want to withdraw some money from it. And I need to make sure, in order to make sure I stay within a positive balance, those operations have to be completed in that order. Well, the way I can guarantee that happens is I just send that actor those 3 commands in that order. And the actor can't move on to processing the second one until it's completed the first. So it gives me some guarantee around ordering in terms of what the actor's expected behavior is going to be. So that's really powerful. The last promise that actors make is an at most once message delivery guarantee. We guarantee that a message will be delivered between 0 and 1 times. So that means there's no duplicates. We don't try to automatically redeliver messages for you or anything like that. And the system will be really fast because that doesn't require much work. So the implication there is if you need a stronger guarantee than at most once message delivery, you have to go ahead and explicitly turn that on in Akka.net. You have to choose to use it. So one of the things that's worth remembering about Akka.net is all of its defaults are designed to have the fewest moving parts possible in order to give you the most speed possible, is what we're trying to do. We call it downhill software development, where all of your design choices as an Akka.net developer all tend to go in the same direction. You're going to be choosing to trade away some of Akka.net's speed and performance in exchange for things that are more important in that context, like consistency, reliability, or durability are all good examples. Does that make sense so far? We're good. The last thing is that every single actor in Akka.net has a unique address. So if I have 100 processes, each running with 1 million actors, all 100 million actors total in my entire network all have at least one globally unique URI that I can use to send them messages directly. So that means that every single piece of state inside our actor system is addressable at any given time. However, most of the time the way we communicate with actors is through a little handle called an actor reference instead. And that actor reference abstracts away the actor's address, so we don't typically need to know about it in order to communicate with it. So these are sort of the core concepts of what the actor model does. And Akka.net is an implementation of this. And Akka.net, being a framework, exposes a whole bunch of different tools designed to make it easy to build either distributed systems using Akka.cluster, or if you want to use Akka.net in a context that's more local, like in a Xamarin application or in Unity 3D or in WPF, you can just stick to using things like the core Akka library or maybe Akka streams if you want. But in terms of the menu of stuff that Akka.net offers, the really big ticket items for doing distributed programming are Akka.cluster, which allows us to build elastic networks of actors that can span multiple computers. And this is typically what people use for building distributed systems with Akka.net. We have Aqueduct Persistence, which provides a CQRS, not CQRS, event sourcing. Provides an event sourcing model for allowing actors to persist their state incrementally. And then we have a couple of other tools built on top of Aqueduct Cluster for doing things like partitioning state in a consistent fashion across the cluster, or doing like decentralized sort of publishing and subscription of topics, sort of like a topic broker. So we have a lot of different tools that are available in Akka.net. I'm not going to spend that much time on any one of them. The really big thing I wanted to show is fundamentally what is an actor and how does it work. Can everyone read this code okay? In the back look good? All right, good. Can I zoom it? I think this is just a little image here, but I can try. Let me see. All right, here we go. I am the man.
Is there,
Here we go.
is there a request for an actor put on a queue someplace, and then something else takes the actor off the queue and then assigns it to a processor?
So the question was, is there essentially like a work queue that basically schedules these actors? And yes, there is. So here's the way to think about actors from an execution standpoint. So this class right here, command processor, this actor inherits from this base class, receive actor. This is sort of the fundamental base class that most people use for defining actors in Akka.net. There's a couple of other base classes, like there's the receive persistent actor, which gives you the ability to save your state and all that stuff. But this is sort of the fundamental actor that people use. An actor, when it has no messages to process, doesn't use any CPU at all. It stays in memory and hangs around, but it doesn't actually hit the CPU at any given point in time. When that actor receives a message, that actor will be scheduled onto a construct inside Akka.net called a dispatcher. That dispatcher, the default one, runs on top of the default .NET thread pool. And it has a sort of just like a fair work queue built into it. And so every actor gets to process a burst of messages before they have to yield the thread and go to the back of the line again. And I think that the burst size by default is 30 messages. So if an actor has, let's say, a couple hundred messages in its queue, it'll process a batch of 30, yield off the queue again, then go to the back of the line, and it'll keep going until it's processed every message in its mailbox. We have the ability to customize the dispatcher. So for instance, we have some customers working on IoT devices where they have to be able to guarantee something like, this actor must poll this buffer on this sensor 400 times a second or we lose frames of data, which represents like a critical consistency failure for us. So in that case, you can use what's called a pin dispatcher, where that actor gets a dedicated thread that it always runs on continuously. So you have the ability to go ahead and sort of toggle some of that stuff if you need to. Typically, though, the defaults work pretty well for most cases. Some of that IoT stuff can have some edge cases in it, though. That's where customizing it makes a little sense. So this actor here has some internal state. In particular, the internal state we have is this iActorRef. This is an actor reference. It's one of the things I mentioned earlier. This actor reference is what allows us to send messages to another actor somewhere else in our system. So it's just basically an interface for communicating with another actor that's running possibly in this process, possibly in a remote process somewhere else over the network. So what's going to happen if I can scroll down here just a little bit? This receive method right here. Here we go. All right. This receive method right here, receive attempt crawl. Attempt crawl is just a C# object that I declared. So basically it's just a type of class in C#. So messages aren't anything special in Akka.net, they're just types. And I have this strongly typed function here that takes a message of type attempt crawl. And we're going to go ahead and do a little bit of checking. We're basically checking to see if this, if the URI they want us to crawl is well formed, kind of a basic validation check. And if it is, we're going to go ahead and format that into a start job command, which we are then going to tell to this command router actor here. Now this command router actor can be running locally inside the same process as us, or remotely in another process someplace else. I'll get into that in more detail in just a minute. But this is sort of the basis of how you communicate with actors back and forth. You'd never have a reference directly to the command processor class. You always have a reference to that iActorRef type. That's sort of the interface we use for sending messages. Any questions so far before I keep going?
How does it know which IACT or ref to pass?
How does it know which IACT or ref to pass? In this case, the parent actor who creates this one basically has another child, which is that command router actor, and I pass that actor into this one's constructor each time. So essentially, every time this actor starts, it always has a reference back to that old previous actor. Now, one other important thing, see this little pipe to down here, or see this sender.tell at the very bottom? Every single time this actor receives a message, that sender property gets changed to be a reference to the actor who sent us the message we are currently processing right now. So if I want to send a reply back to whoever sent us this message, I can just do sender.tell whatever. So in this case, I'm telling the sender that we're starting the job. And this bottom case below, in the else statement there, I'm saying, hey, we couldn't actually crawl this domain because the URI is malformed. Please try again. And in this application, which I'm going to demo a little bit later, that would actually result in an error message being displayed on screen. Make sense? Very cool. All right. Now I'll go ahead and get back here. Now I mentioned that actors have internal state. And internal state is really just properties and fields declared on actors. Well, because of the fact that actors only process messages one at a time, one of the things that this means is that at any given point in time, if I want to read that state from that actor, or if I want to update that state, the only way I can do that is by sending that actor a message. What that actor will do, if I'm reading that state, is it'll go ahead and copy that state into an immutable message and send me a snapshot of what that state looks like at any given point in time, right? Now, if you're worried about consistency, where you say, gee, well, by the time I receive that state, let's say a few milliseconds later, if you're running over the network, if I receive that state back a few milliseconds later and now it's already out of date, what can I do to make sure I always get the most current copy of that state at any given time? And the answer is that actors have really flexible messaging paradigms. In that case, what you'd want to do is you'd want to use publish and subscribe, where I'm going to go ahead and tell this actor, I want to subscribe to you, and every time your state changes, I want you to publish the most recent delta on that back to me. And actors can do this really inexpensively and really cheaply. It doesn't require any infrastructure like an external messaging system or an event bus or anything like that. It's all built into the way actors work innately right out of the gate. So I'll go ahead and give you a little example of that. The code sample that I'm going to be running tonight is our web crawler. This is what we use for teaching Akka.cluster. So I did a demo of this on top of, I think, Amazon Kubernetes service back in February. And I was doing a demo for a big customer in Europe. And I decided to go ahead and crawl a major United States political news website just as a demo. And I accidentally triggered DDoS protection for it. Had the span of about 2 minutes. So I felt pretty proud of myself for that. So this crawler can really scream when it's running on a lot of hardware, or even when it's running locally too. But the thing I wanted to show real briefly is, let me see if I can find it. And by the way, this code is open source if you want to get access to it. I'll pull that up in just a moment. Here we go, that's what I'm looking for. I like it. That's my jam. I'm more of a Rihanna person, but do what we can. So just to give you an example of what pub sub looks like in Akka.net. See this hash set of subscribers? So every single time this actor, this crawl master actor, this actor owns a single domain that we're crawling. So my web crawler could be crawling lots of domains simultaneously, right? I can crawl Wikipedia and Rotten Tomatoes at the same time if I want. Well, if I'm the Wikipedia actor, and I've got a number of other actors that want to know, hey, what's the current status of your crawl? They might go ahead and send me a subscribe to job message, which is what I'm receiving right here. And by the way, actors in Akka.net can receive interfaces instead of concrete types if you want. They can also receive generics, which is pretty fun. So what I'm going to go ahead and do is say, okay, well, I'm going to go ahead and add you to my list of subscribers. And then every single time I receive, I'm just scrolling down a little bit, every single time I receive a crawl job stats message from one of the actors actually doing all the downloading and the parsing, I'm going to update our total statistics and then call this method publish job status. I'm going to iterate over that list of subscribers, which again is just a hash set of actor references, right? I'm just going to tell each one of them a copy of that of my current running status. And voila, we have publish and subscribe in about 12 lines of code. Compare that to setting up RabbitMQ or something else like it, and this is radically cheaper by comparison. And the reason is because this messaging model and the ability for sort of a single point in your system to uniquely identify itself is built into the way actors function. It's the actor references that make all that possible. Now, one quick question. This is more of a kind of distributed programming trivia to some extent. Can anyone think, from a distributed and concurrent programming standpoint, why am I using a hash set instead of, let's say, a list or another type of collection?
Don't send the same message twice, the same person.
So you don't send the same message twice. Hash sets and dictionaries both have a really important property from a distributed programming standpoint called idempotency, which basically means if I perform the same operation twice, the net effect on my state is identical to if I only did it once. What that means is it makes retries really inexpensive. So if I go ahead and send a subscribe message, but I accidentally send it twice for whatever reason, this actor can only add that subscriber once to its list. Therefore, we don't end up publishing that downstream actor 2 copies of every state update. That's a really useful property to have in a concurrent system. All right, so just want to give you a little example of pub sub real briefly before I keep going. Now, actor state is always private, like I mentioned. You can't directly access that command processor or that crawl master actor's state from the outside. The only way you can get access to that state is by sending that actor a message and having it send a copy of its state back. So that's one of the things that helps us guarantee thread safety around actor state, is the fact that it can't ever be concurrently modified or accessed. Now, the next big thing about actors is that they live in a family tree structure. So at the very top of the family tree, we have this user actor. This is the root actor that's built directly into Akka.net. So it's kind of the anchor for all the actors that you can create as an Akka.net end user. And that actor has children. These are what are called the top level actors. These are the actors that you create when you start up your application using Akka.net. So the way actor paths and actor URIs get constructed in Akka.net is incrementally. So this child of the user actor, its full path is /user/A1. Is A1's its name. If it creates a child named C1, the path of that actor will be /user/A1/C1. The kind of purpose of the actor hierarchy in Akka.net is twofold. First, quick show of hands. How many folks in here have played around with domain-driven design before? Okay, I'd say about a third of the room. In domain-driven design terms, the top actor at the top of the hierarchy represents the aggregate root for that domain. And its children represent much narrower bounded contexts is what they do. Now, for those of you who haven't done domain-driven design, I'll give you an example to kind of show you what I mean. If we're back to our oil wells example I kind of cooked up earlier, this actor right here, A1, might own all of the oil wells for a single site in our oil field. It might create a child for every individual oil well underneath it. Essentially, the actor hierarchy gives us a way of naturally partitioning and structuring data and pushing things down. So what that A1 actor might do is it might receive the fire hose of all events coming from all wells in the field, and it'll go ahead and recognize when it sees that, let's say temperature update message, it'll say, okay, this belongs to well C1. I'm going to route that message to that child. Oh, this message might belong to well number 2. I'm going to route that to the well 2 child, and so forth. So the actor hierarchy gives us a way of partitioning state. And the other thing it gives us is a little bit of failure handling. If an actor crashes in Akka.net, let's say, and by crash I mean it throws an unhandled exception, the only thing that affects is the actor who threw that exception by default, meaning that you can't have side effects elsewhere inside your system. When an actor crashes in Akka.net, it's the responsibility of the parent to decide, what are we going to do with that actor who failed? And the default strategy in Akka.net is to force that actor to restart. The kind of error handling strategy that was invented back in the Erlang days for the actor model is called just let it crash. Reason why we do that is because if you go ahead and try to use, let's say, a bunch of try catch blocks to dig your way out of an exception, most of the time you're operating with very limited information on why you crashed and how you crashed. Therefore, anything you're doing in that catch block, more often, other than just simple logging, is probably going to be wasted effort and code that is largely untestable and kind of unknowable. A better strategy, a better sort of generic strategy for dealing with exceptions, is take the thing that threw an exception and reboot it, and then retry it and see if it works, right? Now, if an actor keeps crashing repeatedly, Akka.net will go ahead and say, all right, well, this actor's crashed 10 times in a row, we'll just kill it permanently and assume that there's something really wrong with it, like maybe its state's corrupt, or maybe some external resource it depends on is permanently offline, right? That's kind of built into the sort of Akka.net supervision model. Covered this, all right. Now, the next big thing I wanted to address as part of, we've talked a little bit about actors and how they're structured. Akka.net's a rich topic, so I can't really go into a whole lot of detail in every area tonight, but I will go ahead and give you some resources you can look at afterwards if you're still interested. But the next big thing I wanted to talk about is, from a network programming perspective, message-oriented systems are really robust and powerful. So quick show of hands. Who's done work with something like RabbitMQ or MSMQ or any sort of message-oriented system before? Okay, about 4 or 5 of us. Well, message-oriented programming is something that's becoming a lot more common and a lot more popular because it offers much more flexible processing styles than what traditional request-response programming can do. That's fundamentally, request-response is what HTTP programming is, right? Every single request gets a response back before you're allowed to do your next piece of work, right? Well, message-oriented systems are a bit more flexible, and here's why. Messages in a system like RabbitMQ or Akka.net are typically comprised of 2 parts. The payload, which basically says here's what the message represents. So I think I just knocked out my power by accident here. Plug that back in. The payload basically demonstrates here's what the message represents. And then there's the reply to address. When you're done processing this message, who should you send some sort of acknowledgement back to? And truth of the matter is, the reply to address can be totally blank. If you're doing a fire and forget message where you don't want to receive an acknowledgement back, then you might go ahead and leave that field totally unpopulated. Next, message passing is always asynchronous. If I go and send you a message, I'm not sitting there necessarily waiting for you to reply back to me right away. I might go and do other things while I'm waiting for you to process that message. Now, there are some cases where I can explicitly force myself to wait until I get a reply back from you. That's really useful in situations where you need to do something like commit a transaction would be a good example. Or maybe I need to wait for a user to authenticate before I move on to my next piece of work. Those are good examples of where waiting for a reply to come back is actually a good design, right? Next thing about messages that's really useful is in order for a message to be sent over the network, that message must be serializable. Meaning we must be able to take your message object and represent it as bytes on the network somewhere. Well, if we can serialize a message on the network, we can also serialize it on the file system, right? So one of the things this allows us to do is build event sourcing systems where the way we can go and rebuild application state inside our Akka.net applications is by replaying messages we've processed in the past. So if I want to go ahead and do something like move an actor that has a bunch of critical business state on it from one computer to another, I can do that by killing the actor on one machine, recreating it with the same ID on another, and that actor can replay all of the messages that were saved to its journal back from a database like SQL Server or Cosmos DB or whatever. Next big thing about messages is the order in which they are processed can be changed on the fly if we want. So by default, Akka.net uses first in, first out message processing. But there might be some scenarios where that might not be the best tool for the job, right? One example might be, maybe you want to have a priority for messages, where some messages are more urgent than others, right? Let's say, for instance, if you're building a safety critical system, like maybe an oil field monitoring system, if you want to issue a safety alert because you're seeing some, let's say, bad data coming in from one of your wells or from a pipeline, you're going to want to make sure that message jumps the line ahead of all the other normal messages that are sitting there, right? So you have the ability to go and customize how messages can be processed in Akka.net. And one other really useful feature that we have is what's known as a stash, which is a way of an actor saying, you know what? I'm not in a state where I can actually process this message right now. I'm going to set this message off to the side over here, and I'm going to get back to it later. Once I receive this other piece of data I need from someone else, then I can begin processing it. So here's a good example. If I'm supposed to go ahead and, let's say, aggregate a whole bunch of information and send a report out to somebody, if I'm missing a whole bunch of data points and someone's trying to query me for my state right now, I might have to defer sending them any results back until I get that piece of state I need to do my work, right? That's an example of where deferral of message processing might be really useful. And the last big things that messages can do is, this is something that you can't really easily do in like an HTTP system. If I receive a message, I don't necessarily have to be the one who processes it. I can go ahead and take a look at this message and go, you know, this seems like a better job for actor B over on that other computer. I'm going to go ahead and forward the message to him. He can finish processing the message and send you a reply back. And that's totally normal and, in fact, a very common pattern in Akka.net. The idea of being able to delegate processing of a message to someone else, or the ability to forward that responsibility to somewhere else on the network in some cases. So for instance, Akka.net has this entire routing system built into it, where we can do things like use a routing strategy. Like, let's say I want to route this message to the computer with the most available RAM or the least busy CPU in order to do this particular type of job. And I can go and say, well, that computer's not me. I'm running at 90% capacity. But since we're using auto scaling on Azure, we have this brand new computer over here that's running at 0% load right now. I'm going to go ahead and send this message over to that computer until it's just as busy as the rest of us. Make sense? Any questions so far? All right. So messaging patterns become a really important tool in the context of building a distributed system. So I'll give you a couple of examples. This first pattern is pretty simple: broadcast. Broadcasting is really useful for, let's say, distributing commands across a cluster. If I want to go ahead and do something like, let's say, check the health of all nodes of a particular service, the way I might do that is by broadcasting a heartbeat message out to all of them saying, hey guys, I want to know if you're still available. And if I get a reply back from everybody saying, yep, I'm still able to do work, I know that all those other nodes in the network are still responsive. That's an example of where broadcasting might be helpful. Another example of where broadcasting gets used is for doing searches. If I say, okay, I'm trying to figure out where a particular piece of work is being done somewhere inside our system, and because we recently had a bunch of new nodes join the cluster, I don't necessarily know where that is. I'm going to broadcast to all the nodes in my cluster and say, hey, have you seen this piece of work being done somewhere? When one of them sends me a reply back, yep, I've got it, I've basically been able to complete my search in that case. Our web crawler sample does this in order to prevent duplicate crawls of the same domain, for instance. Another really popular messaging pattern is proxying. This is a type of delegation strategy. I receive a message, but for some reason I can't process it, maybe because I'm not programmed to. I'm going to push that work down to someone else and have them send the original requester a reply back. Akka.net makes this whole process fairly easy. Another really popular pattern we just took a look at: publish and subscribe. If I need to get continuous updates about some piece of data inside my system, publish and subscribe is a much better way of doing that than something like polling for changes, right? Because in this case, I'm subscribed to changes, and so I only get data pushed to me when I actually need it, not when I think I might need it, which is what a polling system tries to do. And then we have messaging patterns like one-way, which if I'm building something like a large-scale analytics system, I can't afford to have really chatty messaging protocols. For every single read inside my system, I might have 25 or 50,000 writes. That's what my last business did. So in a system like that, I'm going to rely really heavily on one-way messaging to make sure that that giant volume of writes can be done really cheaply. So In other words, messaging systems give you a lot of flexible tools you can work with that you don't get when you're working in a pure request response environment. So we can play with these to go ahead and build systems that meet our business requirements without putting a whole bunch of pressure on top of it. So the first really big piece of the pie piece of the puzzle that we got for building distributed systems was actors can manage state really well. The next thing that we get is because of the fact that the way they communicate with each other is through messages, we can manage state in a very flexible, customizable, case-by-case manner. So, the building block that we want to go ahead and use to build a distributed system, a messaging pattern is just a style of communication. A messaging protocol is a domain concern. This is how we're going to solve some specific business issue inside our distributed system. So here's an example. Let's suppose I want to go ahead and write a piece of data in 3 locations inside my system for just availability purposes, right? I want to have 3 replicas of this data at any given time. Because if one replica goes down, rebuilding that state from scratch might introduce a latency penalty our business requirements can't support, right? So we want to have a ready-made version of that state sitting in memory at some point at any given time. Most businesses don't realistically have requirements like this, but indulge me. So what I'm going to do here with my messaging protocol is the first step when I receive this write request is node B is effectively my coordinating node. It's the one responsible for making sure that all the other participants play along according to the rules, which is what the protocol defines. So the first stage is, can you guys accept this write? If both of the other nodes participating in this transaction give me an acknowledgement, yes, this write is consistent with our business rules, we can do it. Then I'm going to go ahead and follow up with, okay, everybody commit. And then at that point, I'll get an acknowledgement back. I'll say, okay, yep, we all committed successfully. If one of the nodes couldn't commit, I have to issue a rollback at that point. What a protocol really is think of it as a little state machine, is essentially what we're describing. We have our initial state, then we have a bunch of intermediate states, and then we have one or more final states where we can't do any more work. Some of our final states will be failure states, where, hey, we couldn't commit this transaction because, let's say, node C disappeared from the cluster in the middle of it, and we had no way of contacting it again, so we decided to roll everything back. Or it might be a success state. Everyone was responsive, got back to us on time, this state was valid with our business rules, and we were able to go and update it. Protocols can range from fairly chatty and complicated ones like this to really simple protocols like an acknowledgement protocol, which is how we do things like guarantee delivery of messages. So I send you a message, you send me a little receipt telling me that you've processed it once you're done. So in a protocol like that, even though it's really simple, it's just 2 messages, I can go ahead and guarantee that all the work I'm sending over the network is getting done, right? So protocols can range from being fairly complex things to fairly simple things. The way we tend to build sort of distributed systems with Akka.net is protocols can be composed together. You can think of them as either really small units of work, like that acknowledgement protocol, to much bigger units of work, like this consensus protocol that we're running here. So the way developers who are starting to work with message-oriented systems start thinking about it from an algorithm standpoint is they're start thinking in terms of, okay, this protocol needs to describe all the different states this operation could be in. And if we have a scenario where, let's say, an operation times out somewhere in the middle, we have to have some rule that says, what do we do with the entire protocol instance as a whole? Do we abort? Do we keep retrying indefinitely? Or do we have some other path we can go down to try to get this work done? That's where we can start introducing some like microservice ideas like partial failure. Okay, I tried hitting the database, but that wasn't available. So my alternative route I might use is to serve up a cached value instead, right? That might be better than failing in some cases. It's kind of a your mileage may vary type situation. But really the big takeaway here is that thinking in terms of this protocol-oriented mindset gives you the ability to start describing how to deal with failures inside your system in a way that sort of individual request response oriented transactions can't really do. So there's sort of a ability to sort of include a much bigger picture in terms of the scope of what your service is doing with protocol driven design. Now, let's see, I'm just going to check what time it is real quick. 8:22. I'm going to go ahead and cover real quickly sort of how actor references work. I'm going to give a brief demo, and we'll take some questions. But the thing I kind of already mentioned a little bit earlier is that actors communicate via these references to each other. You never have a direct reference to another actor at any given time. One of the really important traits of actor references is the fact that they have this property called location transparency. So this is Michael Douglas playing Gordon Gekko, the movie Wall Street, holding a giant 1980s cell phone. A cell phone is a great example of something that has location transparency, and that's probably the biggest piece of business value it provides to us at any given time. Who can tell me what part of the cell phone gives us location transparency? The phone number, that's exactly right. The phone number is a logical address that describes a resource, in this case a person or a company maybe. If I want to give my mother a call, back in San Diego where she lives, I don't need to tell my iPhone how to route packets from where I'm standing right here in this room all the way to where she's standing. AT&T figures that out for me with some degree of success sometimes. But that's sort of the cell network providing me location transparency. It's the fact that I just need to enter in the her phone number, and the network will figure out what are the cell towers that she's closest to and try to deliver my packets to her at any given time. Another good example of a tool we use every day, is just as both software developers and as consumers, that gives us location transparency is the DNS system. If I want to send an email to one of my coworkers, I don't need to basically explicitly know what the address of our IMAP server is and how to route packets from here to there. All I need to know is what is my coworker Isaac, what's his email address, and the DNS system and the mail exchange protocols will figure that out for me. Actor references also have this property of location transparency. An iActorref, like the API master or the download master, that actor can point to someone who's local inside the same process or someone who's remote, and I don't need to necessarily know about it. That actor could be anywhere inside this cluster. By the way, this is what an Akka.NET cluster looks like inside the distributed system. So I'm kind of cutting my presentation a little short here so we get to the demo. But an Akka.NET cluster, what we're fundamentally able to do with Akka.NET is we're able to take a bunch of processes that are hosting Akka.NET actors and network them together into a decentralized peer-to-peer network. And each one of these nodes here, A, B, C, and D, represents a process that is hosting Akka.NET actors. And there might be many tens of thousands of actors running inside each one of these. All of these actors can freely communicate back and forth without ever really needing to know which computer they're on. The underlying Akka.NET framework and infrastructure handles all that address translation and message serialization and routing for them.
Because it's all in the database.
Well, it's all in the actor state, all that data. But yeah, it's all basically baked into Akka.NET's built-in sort of built-in actors and everything else. Now, before I get into my demo, one really important sort of network programming question for folks in the audience here. I mentioned that Akka.NET cluster is a decentralized peer-to-peer network. Why might that be really attractive from a fault tolerance and scalability standpoint? The number of nodes you can lose before it goes down. Essentially what peer-to-peer networks help us create, and by the way, this is becoming an increasingly popular type of architecture, not just with Akka.NET, but with database products, for instance. So for instance, NoSQL databases like Apache, Cassandra, and React are all built as peer-to-peer networks. The new Redis clustering system, I believe, is also built as one. And there's lots of other technologies that are sort of leveraging these peer-to-peer designs.
Cockroach.
What?
Cockroach is an interesting one.
Cockroach, yes. Well, the reasons why they do this is because decentralized designs avoid single points of failure and single points of bottleneck. Because all the nodes participating in the system, assuming they're running the same type of software, can all handle each other's work. So if one node goes down, you lose bandwidth, but you don't lose the ability to do that work inside of the system. Does that make sense? Now, one of the other really big properties of peer-to-peer networks that makes them so attractive from a scalability standpoint is the peer-to-peer networks can change their size at any given time without having to be reconfigured or reprogrammed. It's a function of how peer-to-peer networks work that peers can join and leave on demand. So some examples of peer-to-peer applications that you probably use on a regular basis. Multiplayer video games are a really good example. Quick show of hands, who's played Overwatch before? Okay, only a few of us. Never mind. Well, if you've played any multiplayer first-person shooter or any sort of real-time game going back 20 years, almost all of them use UDP multicast to basically do peer-to-peer networking. That's why if you go and take a look at your game statistics, you'll see a packet loss. That's your first clue you're not running on TCP. TCP doesn't lose packets. UDP can. So they do that because that's a much more efficient way of sending game state and avoiding these centralization issues on the server. So peer-to-peer networking is kind of in vogue. What I'm going to show you next is, let's see, you know what? I'm going to go ahead and kill my little cluster here. I'm going to go ahead and fire up my little web crawler demo. Unfortunately, I presented at a meetup in Austin last night. Not nearly as good as Houston, I should point out. It's not just because I live here. It's because well, you know what? I shouldn't be too mean. They do have really good whiskey bars. I only got a chance to try about 8 of them last night.
Only 8 bars?
Only 8 of them, yeah.
You had to crawl.
Yeah, I had to crawl. Let's see. Here we go. If you want to follow along with this code sample or play with it on your own, you can go ahead and clone it from this URL, github.com/petabridge/cluster.webcrawler. This is our web crawler sample that we've fully Dockerized, and we've also stuck it into Kubernetes if you want to play with it there. What I'm going to go ahead and do is I'm going to go ahead and spin up a brand new web crawler instance using Docker Compose in this case, because it's a little easier. And this is going to form a small Akka.NET cluster. And we'll play around with this for a little bit. For all the improving people, I promise not to get you blacklisted from any important domains tonight. This laptop's not powerful enough to do that in the first place. All right. So let's see. I fired up, looks like 5 nodes here in my cluster. So let me go ahead and this tool, by the way, that I'm running right here is called petabridge.command. It's a command line interface for managing Akka.NET clusters. So it's a free tool. And what I'm going to do is I'm going to go ahead and type this cluster show command here. And what you can see is I have a total of 5 nodes in my cluster. I can see the full address of each node participating in the cluster and its port number. And this setting right here that I'm going to highlight, this little box tracker right here, this is what's called the cluster role for this node. It's basically saying here's the type of work this node can do. So the tracker node builds indexes, the crawler node downloads pages, and the web node is the user interface I can use to access it. Make sense? So if I go to, let's see.
And Lighthouse?
Oh, Lighthouse is basically a seed node, is what that is. It's basically the entry point for joining the cluster. So all the nodes in my cluster join Lighthouse initially. In fact, Lighthouse is also what petabridge.command is connected to at the moment. So what I need to figure out is where my web node is. Here we go. All right. This is our web crawler of doom. So I'm going to go ahead and let's try crawling something kind of small. Do my website real quick. Petabridge.com. So you can see here this little message indicates that I have 1 routee at the moment. Oops. Get rid of that. I have 1 routee. We've downloaded 295 documents, 158 pages, and 137 images in the span of about 9 seconds, roughly. Okay. Well, and we did that with exactly 1 crawler running at any given time. If we want to see something a little bit more fun, let's go ahead and crawl a much bigger domain. MSDN did not have DDoS protection for a long time, so that was a good choice. docs.microsoft.com is a little bit more aggressive, but yeah, you know what? Let's give it a shot. Hope your students aren't using .NET improving. Now, one of the things I'm going to go ahead and do real quick while that's running is I'm going to use Docker Compose to go ahead and scale my crawler services up. Let's see. Is it crawl service? Yeah, it is. There we go. So I'm about to fire up 2 more instances of the crawler service. I'm going to do cluster.show real fast. And you'll see that we have 2 nodes that are joining at the moment, right? Y'all can see that? These are the 2 brand new Docker containers I just spun up. They both communicate with Lighthouse, and then Lighthouse introduced those nodes to all the other ones in the cluster. And now they're up and participating. And what you'll see actually, if I go ahead and take a look at the logs, is those 2 crawler nodes are now also participating in this crawl. I basically just brought in a bunch more compute power to work on the same job that was already in progress. The way the sort of architecture of this application works is the tracker node, when it basically learns about new web pages coming back and forth, sprinkles out all of the basically different URLs that still need to be crawled out to all the different crawler nodes that are available. And they can leverage up to 10 crawler nodes in parallel at any given time. So let's see. Looks like I've hit the point where DDoS protection is turned on now that my crawl has stopped here. Usually I get to about 17 or 18,000 pages before that happens. Though if I pull it up here,
it's effective.
There you go. All right. Well, that's the end of that. That's the end of the crawl. But if we go and take a look at some of the source code here, it'll reset in plenty of time. I'm sure it'll be fine.
I don't know. Like,
could you have gone through a proxy?
I kind of did through Docker, but yeah, that's just a local one though. I'm sure it'll be all right. I do this from my home computer all the time. So this right here is the configuration format that Akka.NET uses. If you want to go ahead and use clustering with Akka.NET, one of the things that you'll do is you'll go ahead and say, all right, the provider that we're going to go ahead and use for Akka.NET is the clustering provider. This is what's telling Akka.NET to go and load all the clustering code at startup. If you don't include this line of configuration, clustering never loads. But the thing I wanted to show down here is this is a broadcast router. This is a special actor that could go ahead and broadcast messages to all the other nodes in the cluster that have that tracker role enabled on it. And we're going to go ahead and deliver those messages to this actor at this path, /user/API up here. And I can also create routers like this one down here that route messages using a round-robin strategy to this crawler node. If I go into my little tracker service here, what we end up doing to go ahead and actually run this application for real, is I create an actor system, which is basically the fabric that hosts all of our actors. So an actor system is kind of the thing that allows actors to talk to each other. And I'm going to go ahead and pass in my Hocon configuration that I parsed from this file here. Hocon is essentially typed JSON is what it is. The acronym is terrible. It stands for Human Optimized Configuration Object Notation. I didn't come up with it. And then down here, I dig it. Then down here, I'm going to go ahead and call, whoops, let me go back real quick. Go back to the tracker service. I'm going to go ahead and start an actor by calling props.create, and I pass in a little new expression to say how to create this API master actor. So Akka.NET's a port of Akka from Scala originally, and it took me about 2 years to figure out that the reason why this is called props is because actors need props in order to act on stage. So I figured it was like short for properties or something. But when I pass these props into the actor of method, this is how I get an actor reference back. This is what starts the actor and allows it to begin work. This API master actor will down here go ahead and create this line of code. See this context.actor of call right here? This is how you go and create a child actor. So I'm going to go ahead and call context.actor of to create a child. And this child is going to go ahead and be a router here. I'm basically saying we're going to go ahead and create a router from our Hocon configuration And this child is going to be named after this sort of master broadcast actor. That actor is essentially going to be this one right here. It's a little clustered broadcast router we're going to use to talk to the rest of the cluster, is what's going on there. And I'm going to be able to use that actor to go and talk to all the other nodes that are running the tracker software to figure out whether or not there's another instance of this crawl job running anywhere else inside the cluster. And you can see down here that I've got another router we create a little bit elsewhere in this program that lets me talk to crawler nodes. This is how I'm actually facilitating the cross-process communication in Akka.net. Now, I'm going to go ahead and stop here for the evening since I don't want to keep us all too late. But I will take a couple questions and a couple things I want to plug before I do. We are, if I go ahead and pull up Petabridge's Twitter. If you want to learn a little bit more about Akka.net, you can go ahead and follow us at Petabridge on Twitter. Let me go ahead and get rid of this. Now, one of the things, if you want to learn Akka.net for free, if you have some self-paced lessons, we have this free Akka.net bootcamp that you can go ahead and take at learnakka.net, this URL here. It's basically about 17 sort of self-paced courses. You'll learn how to build Akka.net applications locally. So we have you build like a Windows Forms version of Performance Monitor on your computer using Akka.net. So that's pretty fun. But the other thing I wanted to introduce is if you go to our Twitter account and go down here, we're actually hosting, I don't have like a nice tiny URL for this. We're actually hosting a free webinar on Monday on Akka.cluster and Kubernetes, how to do continuous integration with Akka.net. So if you're interested in learning a little bit more about how to use it in a real professional like business context, I definitely recommend attending that. We're doing it at 10 a.m. Central Time on Monday. And the full URL for that, go ahead.
Can you email that to me and I'll post it on the group's Facebook?
Absolutely. I'll go ahead and send that to you. That'd be perfect. So we're doing that on Monday. And then since we're all right here in Houston, one other thing I should plug real quick before I take some questions. Here we go. I'll go ahead and send you a URL for this too. We're actually doing 2 days of on-site training at the end of May at the Sam Houston Hotel in downtown on if the things you learned from the webinar on Monday, if you end up signing up for it. We're going to be doing a hands-on workshop where you'll get a chance to learn Akka.cluster, Docker, and Kubernetes and how to combine all those together over the course of a couple days. So that's my plug. Yep, go ahead.
Can children from different parents communicate with each other?
Absolutely.
Okay. What kind of issues are there with message overload in this kind of system?
What kind of issues are there with message overload in Akka.net? So in memory, Akka.net actors on a D2, V2 Windows Azure VM can process about 4.5 million messages per second. That's just doing sort of like the raw Akka.net sort of forwarding and routing type stuff. If your code is a little bit more expensive, let's say you need to do something like make a network call inside your actor, like you're writing to a database or a file or calling a web API, then the actor is going to be considerably slower than that.
I mean, receiving messages is one thing, but you have to process all those messages, and so you could the actor could end up with backlog.
It could. So we do have some tools for working with sort of back pressure there. Akka Streams is the biggest one. That's basically uses Akka Streams uses a protocol called a reactive stream, where essentially the downstream actors can tell the upstream ones, I'm running behind on all this work. I need you to hold off on sending me any new work for the time being, or I need you to start batching it.
Somebody else.
Yeah, or send it to somebody else. We also have routers that have the ability to do things like route this message to the actor with the smallest mailbox.
So the parent, in that case, might spin up another actor.
Yeah, exactly. You can go ahead and basically scale up more actors on demand. Actors are a very cheap resource, so they don't take up very much memory, and you can actually spin up about 50 or 60,000 actors per second pretty reliably from like one parent. Yes?
How does it work with microservices architecture?
How does actors work with a microservices architecture? Well, you know those roles I was showing a little bit earlier here in Petabridge.command? These are effectively services, in other words. So the way to think about it is actors themselves aren't necessarily, they're like a much smaller unit of work than a microservice, But each one of these nodes in the cluster can be a microservice. So in other words, they're communicating using the Okadot remote protocol over TCP, rather than using something like HTTP. And they're typically spinning up and down, sort of using sort of a peer-to-peer networking system rather than client server. But fundamentally, you can build microservice architectures using Okadot cluster.
I have a question. Before you said that one actor can proceed like people, one by one, messages. But let's assume that for one message it takes a long time to proceed, and many messages come. Where are they stored?
Those messages are stored in the actor's in-memory mailbox, which is basically just a concurrent queue.
It's just a concurrent, but the actor owns this queue or not?
The actor owns the queue.
Okay.
So think about it like rather than one giant queue, every actor has its own personal queue that belongs to it. So it's basically like millions of small queues at any given time. And most of these queues tend to be pretty empty for the most part. But if you have one actor, let's say, gets backed up processing a really complex message, as soon as it's done processing that, it'll have a chance to go and work through the rest of the other messages in its backlog. Now, in the event that you have a message that takes a really long time to process every time, the right way to usually handle that is to have that actor spin up a task to go and process that message, and then have it when that message is finished being processed, have it pipe the result back to itself. That way, the actor could go ahead and cancel processing if it needs to, using a cancellation token or something like that. Yeah. Oh yes, go ahead.
When we spread these actors across different machines, does it take care of all domains? Make sure that they're not on the same node or something? Got it.
So the question was, when we spread actors out across different machines, is there a concept of fault domains to basically make sure that not everything's clustered together? One of the things that we're going to be adding to Okadot Cluster in the near future is the ability to describe data centers in there, where you can essentially hint this actor is in a totally different rack than this one is, and they'll have the ability to go and explicitly describe that right now. Otherwise, the distribution, you can basically say, I want an even distribution of actors across all nodes of the same type. And the Okadot cluster system has no way of knowing who's physically co-located on what rack or not under that set of circumstances. So we're working on adding that feature right now to go ahead and basically give you the ability to describe that. And that's really useful for like multi-data center type work, or if you want to go ahead and use multiple data centers for like fault tolerance purposes, even if you're running locally all in one spot. That's a good feature for that. Do you have a question?
Yes. As you were speaking through your presentation, there's many things that sounded familiar to me in terms of Tony Hoare's article on communicating sequential processes. Is this a completely different approach based upon a different paper, or are there similarities?
There's definitely similarities. Because all of these actors are essentially sequential processes, right? Each one is processing its messages in sequence. And they're communicating with each other via message passing back and forth, which I haven't read that paper, but it sounds like, based on its title, fairly sort of similar in scope.
Well, I think Tony Hoare's article was mainly about tightly coupled systems that work synchronously, whereas this is more of an asynchronous one.
Yes, it is, yeah.
And so the point of communication and communicating sequential processes is that processes synchronize in their communication, and they don't have buffer overflow issues.
Gotcha.
Because they run synchronously.
Got it.
Carl Hewitt
Yeah. Oh, okay. Gotcha. Yeah. So so actually one last thing. I've got some Okadot stickers I'm going to set down on the middle table here. Love it if you all took one. We order hundreds of these, so definitely spread them around. But otherwise, thank you very much for your time. I hope to see you all again in another meetup in the future. And if you have any questions, I'll stick around for a few minutes. But otherwise, thank you for hosting me. I really appreciate it. And I'm looking forward to participating more in the local .NET Houston meetup scene. Thank you.
Thank you for joining us for the March 2019 meeting of the Houston.NET Users Group. Our meetings are held on the second Thursday of every month at the Improving Houston office at 10111 Richmond Avenue. Be there at 6:30 as we kick things off with pizza and prizes. If you happen to be in Houston on any second Thursday of the month, we would love for you to join us.